But regardless of your personal circumstances, we've got some three more very interesting talks for you. The first is a low randomness second order masked AES implementation. So if the presenter is ready to share their screen and take it away.
Yes, definitely.
Okay, great.
So let's see, is this visible?
That's great.
Perfect. So yeah, thanks. So this was a work done together with my colleagues, Tim Bijna, Adriaan Ranea, Daniela Cicek, and myself, Simon Doge. And this will be on side channel analysis and masking and higher order masking. So yes, so let's see. Basically in 2020, in AsiaCrypt 2020, we made this theory to have a security analysis that allows for the creation of maskings, higher order maskings that don't use much randomness. And back then that was applied to the LED cipher. And now the idea was, okay, let's see what happens with AES. And we found that masking the AES actually poses a lot of new challenges. And that was a way to basically improve our theory. So one of these challenges was that the SBox doesn't have a uniform sharing. So we have to use the changing of the guards method. But this method is typically used only in first order security. So we had to analyze it in second order security. And essentially it changes the diffusion of the masking. And that's actually important because from this theory, we are using linear cryptanalytic methods to analyze the security. So the diffusion is actually quite important. And that also meant that we weren't able to do this security analysis by hand anymore. So we had to use something like SMT solvers, something more modern, let's say. And then we got a bounce from this. So we had a bounce on the adversary. And we found that this bounce was actually, like a big chunk was taken out of it from the ideal nature of the glitch model. And basically we challenged that idea. We said, well, in reality, glitches are not going to be as devastating as what we're assuming now. And we just had the question, can we get theory to practice? So let's say that you did a lot of practical experiments, and from that you would decide that actually glitches were much less detrimental than what you thought. Can you put that into theory? And at last we made a master AES, but it was still using a lot of randomness. So we looked into ways of reducing or amortizing randomness. So a few of the most important things are this changing of the guards. So this changing of the guards basically chains SBoxes together and creates kind of diffusion patterns like shown here. And we wanted to improve the diffusion. And what we did was we applied this to kind of simulate a Randall 160 like diffusion, where we chain SBoxes over rows with an increment depending on the row, which creates this extra column. And also with this extra column, we apply an extra mixed columns operation. So this gave us much better diffusion. And with SMT solvers, we're able to look at the trails we have through the masking. And so this is an example of the best trail we could find. And this would give us the security claim. So basically it gives us a bound on a second order probing adversary. But again, this bound, we weren't exactly content with it. So we implemented the AES SBox, our masked AES SBox for, well, in simulation. And we checked, well, what can you view with a probe? So how do glitches kind of react in this implementation? And we took a look at the Fourier distribution. And normally, whereas in theory, you would say that a probe would see 24 bits of information, actually here with our simulations, we saw that the worst case scenario was that you see something like 11 bits of information. And we're also able to plug that into our theory that, well, if you believe these experiments or you did these practical experiments, you did that effort, you can actually validate that in theory as well. So you're able to sharpen it and get a bound that would be closer to what you would see in reality. And then finally, what I said before is that, well, our masked AES still uses a lot of randomness, but our masked AES was actually functioning cryptographically strong. So the question was, can we put this in some sort of feed-forward mode? Can we have multiple masked AES calls and somehow extract some randomness from the first masked AES call to be used for the next? So we use this simple structure, let's say, and again, in the theory, you can look at our work as a bunch of security claims. Again, we see, well, okay, we have a new bound on our adversary where L is the number of masked AES blocks that you bundle together, which are using each other's randomness. So that's in a nutshell our work. Thanks.
Thank you. That's great. Should we save the questions for the end? I think when we've got all of the speakers together. I know you have one question already, but we'll address it after the other two talks.
We can continue with the others first, yes.
Yeah. So the next talk on the arbiter puffs and how they sample the Boolean function class. Whoever's presenting. Okay, that's great. Thank you. Take it away.
So, is my screen visible?
Yes. Yes.
Yeah, that's great.
Okay. 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 Thank you. So this is a joint work with Onimes Roy and Subhom Mitra, and the title of the talk is the How do the arbiter puff sample the Boolean function class. So arbiter-based puff is a pseudo-random bit generator. It takes a challenge bit. If it is of length n, so it takes a challenge bit of length n and generate either 0 or 1. So it has a circuit, and in all the stages, you can see that there are two paths. One path is top path, another is bottom path, and all these paths are associated with some delay parameters. And the randomness in the outputs comes from that delay parameters only. So depending upon the delay between the top path and bottom path, that arbiter either output at 0 or 1. So if it is the delay is less than 0, it outputs 0, and if it is greater than 0, then it outputs 1. So it can see that this is basically a Boolean function involving a number of variables. So in literature, there are multiple results which try to analyze this kind of structure, and it has been observed that it has many non-randomness. Now, if we just look into the autocorrelation distribution of this arbiter-based puff, we can see that if I consider a 4-variable Boolean function and 4-variable puff, their distributions are completely distinguishable. So now from this distribution, one might think that, okay, can you say anything that what class of Boolean function is generated by this arbiter-based puff? So we address this question in this paper, and also there was a huge bias in the output. If I take two kinds of input into the arbiter puff, so we have tried to minimize that bias by considering the domain to be a restricted domain to the arbiter puff. So we started with the n is equal to 1, and we have seen that if I take an 1-length puff, it will generate all such Boolean functions, so that both these two sets will be exactly same. So now the interesting thing starts happening from n is equal to 2. So for n is equal to 2, you can see that there are only 14 number of Boolean functions which can be generated using 2-length puff, and the two Boolean functions which are not possible which is not possible to generate from 2-length puff is f1 and f2, whose truth table is given in this slide. And from this truth table, you can see that f1 and f2 both are complement to each other. And from this result, we have proved that if an Boolean function f involving n number of variable, if it is not present in the set of Boolean function generated from an n-length puff, then its complement will also be absent. And we have shown that if we have an n plus variable Boolean function, we know that it can be represented in a concatenation of 2 n variable Boolean function. Now we have proved that if we have a function which is not present in the n variable Boolean function, n variable class which is generated from n-length puff, then if I take any random Boolean function and concatenate with that f1, then that Boolean function will be absent in the n plus variable class. So that n plus variable class means it is generated from n plus 1 length puff. Now one might be thinking that if I just take two Boolean functions which is in the class of n variable puff, So if I concatenate them, whether they will be in that function will be in the set of n plus variable class or not. So to answer this question, we have taken two functions f1 and f2, which are present in the set of all Boolean functions generated from two length path. Now, if I concatenate them, then they will be absent. So we have proved that result, and that means if I take any random functions which present in the n variable set, which is generated from n length path, and if I concatenate them, then there is no guarantee that their concatenation will also belong to the n plus 1 length path set. We have enumerated the set of all Boolean functions can be generated from n length path from n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. And from this table, you can see that cardinality of the Bn path set, that is the set of all Boolean functions generated from n length path, is much smaller than the set of all Boolean functions. Set of all Boolean functions generated from it's an invariable Boolean function. You can see that. So from this thing, we have proved that if I take the cardinality of the set of all Boolean functions generated by n plus 1 length path, so it will be less than is equal to the square of the cardinality of the Bn path set. Now for n greater than is equal to 4, we have shown that Bn path, that is a set of all Boolean functions generated from n length path, it is basically a negligible subset of the total Boolean function set. So now one might be thinking that how do we generate this class of Boolean functions from that n length path? So if we take the delay parameters randomly and enumerate the set that set contains the Boolean function generated from that n length path. So in this way, you can enumerate the set. And another way is that if we take the set that which is a set of all Boolean function generated from n length path, and from that set can we iterate the other set. So in our paper, we have provided an algorithm by which you will be able to construct the Bn plus 1 set when the Bn path set is given to you. And now in the next part of our paper, we have defined the restricted autocorrelation, and the definition of the restricted autocorrelation is given in this expression. And here restriction is mean that we are considering the inputs. If we are considering an n-length input, weight is fixed. So what do we mean by weight? So we are considering the input from a domain -1 whole per n, where weight we are defining that it is a number of -1 present in the set, present in that string. Now, if I consider this domain and restricted domain and measure the autocorrelation of Boolean functions and the Boolean function generated from the n length path, then you can see that their distributions are very close to each other. So that means that the issue in the distribution, the autocorrelation in the complete domain can be optimized for this kind of restricted domain. So they are very close to each other. And in fact, if you plot the probability for a probability that zc is equal to zc tilde, where c and c tilde two inputs from that domain enk, which is a domain of restricted weight, and if we fix the weight for different k and check the probability, then you can see that the probability is almost close to 0.5. In fact, we have proved that the average expectation of that autocorrelation over the restricted domain is very close to 0.5. In fact, it is equal to 0.5 for the function which belongs to the set of Boolean function generated from n length path. And this is the conclusion. So we have studied certain limitations of arbiter-based path. In fact, we proved that the set of all Boolean functions generated from n length path is a proper subset of the set of all Boolean functions for n is greater than 1. And we have also shown the existence and non-existence of Boolean function in that set. And in fact, we have shown that using n length path, you can only generate a very negligible class of Boolean functions involving n number of variables. In fact, in the last part of our paper, we have improved the autocorrelation property of the Boolean function generated from the path if we just consider the weight to be a restricted domain. So that means we are considering weight, we are considering input of fixed weight. Okay. So thanks for your attention.
Okay, thank you very much. It's really interesting. We'll look forward to some questions in another 5 minutes. If the final speaker on MPC for Q2 axis structures over rings and fields can load up the screens. Okay, thank you, Barry. That looks good. Go ahead.
Hello, everyone, and thank you very much, Benjamin, for the introduction. As many will be aware, in MPC, we attempt to securely compute functions which input with inputs by sets of parties without revealing any information to the parties except what can be learned from the outcome. In this particular paper, we focus on access structures, which are called Q2 access structures, which means that we have an access structure such as this one, which dictates the qualified sets, those that can reconstruct the secret, which are colored blue, and the unqualified sets, those that cannot, which are in red. Then for a access structure to be Q2, no two unqualified sets can cover the whole player base. In this case, that is the case. In this paper, my co-authors, Robin Jadot and Nigel Smart and I, analyzed the current state of the art and generalized the approach so that many, if not all, practically applicable schemes for Q2 access structures can be realized not only over prime fields and integer rings modulo 2 to the k, but any prime power ring. To do this, we show that all protocols that are usually used in these schemes can be extended to the prime power rings using a Hensel-style lift, which allows us to go from any ring, p to the l, to p to the k for any l and k, a non-negative integer. The fact that they exist does not mean that they are also effective and efficient, but that is also achievable through the use of the Schwarz-Zippel lemma. This gives us a probabilistic measure for us to achieve statistical security over any of these rings. To give an indication of this, we see here one of the post-processing protocols we have worked with, which we called MolCheck1. Without going into too much detail, due to the time constraints, note that this takes as input two triples, x, y, and z, and a, b, and c, for which it should hold that x times y equals z, and similarly, a times b equals c. That is, they are passively secure. So unless an adversary cheats, this is a true fact. Both of these sharings are made modulo p to the k plus v for some security parameter v to obtain either an abort signal or, in the end, the guarantee that x times y equals z modulo p to the k. This triple is then actively secure with abort. So even if the adversary cheats, there's nothing really they can do about the multiplication. This has a few parameters included, which, when chosen appropriately, reduces near exactly to that of the well-known KRSW protocol, with the one exception that we are able to batch some of the open to alls together, so we only need to account for 2 open to alls in communication instead of 3. This leads to the final promising table, where we indeed compare 5 different protocols, each equipped with a choice of pre-processing, multiplication, and post-processing protocols. To give a little bit of insight, Protocol 1 uses an actively secure pre-processing phase followed by a simple beaver online. This requires no post-processing whatsoever because that's done in the pre-processing phase. Protocol 2 uses the optimistic approach posited by ECO20, doing a passively secure offline and online phase to execute the multiplication and then checking with MolCheck1 post-processing. Directly analog to this is Protocol 3. This uses a slight variation of the MolCheck that we've just seen. See the paper for details. However, this protocol, the variation, has no need for an offline phase. So no pre-processing is done in this protocol. Protocol 4 uses an ABF17 style cut and choose, which is far too involved to explain in 5 minutes, but is explained further in the 20-minute presentation and the paper. And lastly, there's Protocol 5, which uses the compute twice technique by Yehuda et al., which is actually the most promising technique, as we can see in the results. This is part 1 of the table, showing Protocol 1, 2, and 3. Here we see the data costs for online and total cost of each of the protocols, which gives us a clear winner in the online phase, which is the blue line. That is Protocol 1. While for the total cost, we see that Protocol 5 in gray is actually the most effective one for the most interesting cases, which is the rings modulo 2 to the k and rings modulo p to the k. When considering total cost, it actually shows that it can be up to 70% more efficient than all other comparable protocols. Thank you for your time.
Thank you for the presentation, and thank you to all three speakers for some really, I mean, you've done a really good job in the limited time that we give you.
I'm maybe the only one, but I can't hear you.
I can hear Benjamin.
You can hear?
Yeah.
Okay.
Yes, you are audible. You're audible.
Yeah.
Okay, that's good. Yeah, this upgraded Zoom tends to reset my sound all the time, so I might drop out. Okay, so I just wanted to say thank you to all three of you for some very good short talks. We've had a couple of questions that we'll get through before the final remarks. First of all, Srinivas had a question for Simon. Does your technique extend to other S boxes?
Yeah. So thank you for the question, and definitely tell me if you want me to answer a specific technique from this. But basically, we wanted to do our work so we worked specifically to the AES because we wanted to protect the advanced encryption standard instead of protecting general ciphers. But we also did this with the idea that you can change the masking of the S-box so that you just allow for different maskings. So the three techniques that we introduced, which was to work with this changing of the guards, to amortize this randomness, and also to look at the glitch models. This is something that works for every cipher, every masking. But yeah, it would be interesting also to see different masking techniques for the S-box of the AES also.
Yeah, thank you. We've got, I think, a really good question from Watson Lad for Dibyendo. It seems like you're considering an idealized model where all the path has is a delay and the switches work the same way in both directions. So how much do manufacturing imperfections actually change that?
So in our paper actually, so what we are doing, so we are showing some kind of existence of Boolean functions and some kind of non-existence of Boolean function from the n-length path. And to prove that thing, we are considering that if you go through the proofs, then in the proof
For me, I lost him. Just
yeah, that
reference.
Answer seems to have been so massive that it's broken the internet. So maybe, well, hopefully Dibyendo will be back and we can get the end of the question. In the meantime, while we're waiting, I've got just a really quick and kind of naive question for Barry. I mean, you've shown that basically finite rings are possible and that we can work with all these different finite rings. But I mean, the last table is pretty massive. And so like, what are the good rings? You know, like if someone can do 2 to the 8, 2 to the 16, 2 to the 32, 2 to the 64, I guess, modeling these different architectures, what is it better to use from your perspective? What are the good rings?
So the rings that we've done a little bit of testing here and there, but we've mostly been focusing on the ring that's 2 to the 128. So it seems to be extremely efficient for rings of the form 2 to the 2 to the k for some integer k. Further, we have not really checked the p to the k versions because that makes the arithmetic a lot harder.
That's fair enough, I think. Okay, thank you. So, Dibyendo, you're back now. I think you sort of disappeared halfway through the answer. But you seem to have frozen again. So, it might be a bandwidth issue, or it might just be it might be fatal. I hope not. But we're also arriving at 7 o'clock, well, 7 o'clock CET, which means we're getting to the point of the final remarks for the conference. So on that note, I guess I want to say thank you again. You're back?
So I'm not sure whether I was audible or not.
So basically your connection just froze and we couldn't hear the end of your answer to the question.
Okay, so
but
let
we'd love to
me
hear
give the
it.
answer.
So go ahead.
Yeah, so if you go through the papers, we have shown certain kind of existence and non-existence of Boolean functions from that in-length pub. And what we have shown that if we consider a 2-length pub, then if we assign the truth table of that to Boolean functions, so for that Boolean function, you do not have any kind of delay parameters. So that Boolean function cannot be generated using 2-length pub. So this kind of result we have proved. So that means we do not have any delay parameters which can generate all that class of Boolean functions.
Okay, thank you. I've just got one very last question that probably has a very short answer. I mean, in your model, you've shown that very few Boolean functions are puffs. And I mean, maybe once you've shown that some are not puffs, it's not surprising that many are not puffs. But still, I mean, you've got a precise formula in your paper. But I'm wondering if in your investigation, you found that actually there are more functions than you expected are puffs or fewer? You know, there are not many, but is it surprising in one direction or the other for you?
Yeah, it's a very negligible class of that n variable Boolean function. In fact, if you see the table that for n is equal to, if I am not wrong, so for n is equal to 3, you can see that there are only 1004 Boolean functions can be generated from 3-length pub. So it is less than 2 to the power 8. So for n is equal to 4 also, it's much smaller than that total number of Boolean functions.
Yeah, but I suppose you weren't expecting everything to be a Boolean function.
Yes. Yes.
And
yes.
did you find out that this quantity is smaller than you were expecting or bigger than you were expecting?
No, these are the exact number. These are the exact number for n is equal to 1, 2, 3, and 4.
I just mean with respect to your expectations before you actually did the scientific part, you know, going into the into your investigation.
So there was huge amount of bias. So in literature, there are some results which prove that pubs have good amount of bias. It's a huge. In fact, if you go to that 2019 IndoGrid paper that was written by us only, so we have shown that there is a bias if I consider 2 inputs which are differing at the first.
Okay, thank you. We're out of time, I think now. So thank you once again to all 3 speakers in this session. And at this point, I'll hand over to the organizers for their concluding remarks.
So thank you, Ben. There's no big concluding remarks. So in the name of Riham, who has her kids at home, and so I will do this alone. And myself, I want to thank all the speakers and to all the program committee members, especially those that actually acted as session chairs. Thanks a lot for this. It is nice that even though it's online, we still have quite some participants, although I think the online fatigue slowly sets in more and more. And I guess hopefully we see each other on a conference very soon, maybe next year's SAC, or maybe even earlier. And I think that's it from my side, and thereby we're closing SAC for this year. Thanks a lot.